Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's SecurityBoulevard.com webinar, brought to you by Techstrong and SciCode. My name is Cody J. Brown. I'm the host of Techstrong Learning. We have an exciting presentation ahead of us, but first I have just a couple of housekeeping notes. First off, today's session is being recorded, so if you miss any of our session or you'd like to rewatch it, the on-demand recording will be made available shortly after we conclude our live session today. If you have any questions, we want you to direct those to the Q&A tab. And that's also on the right side of the screen where you'll find the chat tab. And we want you to use that to engage with your fellow audience members. Finally, at the conclusion of this webinar, we will be giving away 4 $25 Amazon gift cards. So be sure to stick around. So our topic today is GitHub Actions and code injection, avoiding vulnerable configurations. And I'm joined today by Alex Ilgaev, a senior security researcher at SciCode. Alex, thank you so much for being with me. I'm going to give you the floor.
Thank you, Cody. So as Cody introduced me, today's webinar topic will be really GitHub Actions and code injections, avoiding vulnerable configurations. During our next 25 minutes, we'll present our latest unique research on possible code injection or GitHub Actions. So let's start with the agenda. First, during the talk, we'll explore what is GitHub Actions and why is it a powerful build system. Later, we'll learn what kind of misconfigurations it can have and how an attacker can leverage this into a code execution. Then we'll explore the risks of compromised pipelines, including 2 demos. And at the end, we'll learn how can we mitigate these issues. So I'm Alex. I'm senior security researcher at SciCode. Previously, I was investigating malware threats and campaigns at Checkpoint Research. I love anything that relates to security and hacking, so don't hesitate to reach out at me through Twitter. So what is GitHub Actions? For most of its history, GitHub was all about storing source code. In 2018, they announced that they are going in a different but related direction by launching GitHub Actions, a CI/CD, continuous integration, continuous deployment platform, allowing GitHub developers to automate development workflows easily. Since then, GitHub Actions have become extremely popular, mainly due to its rich marketplace containing more than 12,000 actions and free hosted runners for public repositories. By now, GitHub has over 73 million developers and more than 200 million repositories. Almost any language or environment has an action that can help you to automate your workflows regarding that environment. Before we go deeper into the misconfigurations we found, let's understand first the possible usages of GitHub Actions. Some of the usages may be building the code into a container and upload it to the chosen registry. It could be Docker Hub, Artifactory, ECR, GCR, or any other registry. It could be creating scheduled tasks that scan vulnerabilities in code. It could be running tests for pull requests. It could be automatic labeling for issues, which could be based on predefined logic. It could be sending issues to ticket handling systems like Jira, Monday, Asana, etc., and much, much more. So how does GitHub Actions workflows look like? First of all, it is a YAML file and contains a name, in this case, GitHub Actions demo. It contains a trigger event on what event we should trigger and run this pipeline. In this simple example, it will be a push to the repository. And finally, it contains a list of jobs. In this example, we have one job that's called Actions Hello World, which contains one step that echoes Hello World. That's it, simple as it sounds. So to understand the vulnerabilities, we need first to understand some core mechanics of GitHub Actions. The entity that runs the job is called a GitHub runner. This runner fetches the job from the GitHub Actions service and executes them. The runner could be run either on a GitHub hosted machine or a self-hosted machine. If GitHub hosted machine is used, it will also run as an ephemeral environment. This means that each job will run on completely clean virtual machine-based isolation, VM isolated machine. And once the job is over, the environment will be completely deleted. In addition, for each job, GitHub creates a temporary GitHub token. This is how it's called, which can be used to access GitHub API for various tasks. Such tasks could be updating issues, comments, pull requests, code, and more. The default permission for GitHub token is read and write for most of the events. Another core mechanic of GitHub Actions is secrets. Using secrets is an integral part of creating meaningful GitHub Actions workflows. Example for such secrets could be cloud tokens, such as AWS, GCP, Azure tokens. It could be artifact registry tokens, such as Docker Hub or Artifactory, and etc. GitHub separates these secrets into 3 layers of exposure: organization level, repository, and repository environment. Secrets defined on an organizational level are exposed to all the repositories and all the actions in these repositories in the entire organization. In addition, as we talk later in the mitigations, each such secret could be exposed into specific repositories in that organization. The second layer is a repository secret. These secrets are exposed to all the actions in that repository. And the third layer is repository environment, which we'll cover later in the mitigations part. Now that we learned what is GitHub Actions and why is it a powerful build system for pipelines, let's understand what is code injection. We created a simple workflow that does the following. It will be triggered whenever a new issue is created, and it will run the following bash script. This script will check the issue title, and if that title contains the word bug, it will talk with GitHub API and update this issue label with the word bug. This could help the maintainers of the project to prioritize the issues. In this workflow, we can see these curly brackets, double curly brackets. This is another mechanism of GitHub Actions, which allows workflow developers to use additional information that comes from the triggered event. In this example, we have several such usages. We have this one, which will receive the issue title. We have the second one here when we fetch the GitHub token secret. And the third one here when we getting the URL for the issue, so we know for which URL we should invoke the API. Behind the scene, the GitHub Actions replacing these curly brackets with the actual values. So the runner will have the real script. So on the first sight, this workflow looks innocent, but a malicious title could actually alter the bash script and run a control code. For example, if we'll insert this issue title, we'll actually insert code into the bash script, and we'll run this pretty psycho text. This is just a demonstration for our ability to execute code on the runner. Insane, right? So you may think this is a bug, but not only it's not a bug, it was even mentioned in GitHub documentation. It says that when you create workflows, you should always consider whether your code might execute untrusted input from the attackers. So we went into a research to understand how widespread is this issue, and we discovered this is really widespread, and the amount of repositories vulnerable to such injection was really tremendous. We identified dozens of repositories which share this vulnerability in their GitHub Actions workflows. For each such repository, we reported it to their maintainers, and they fixed it almost immediately. Out of these dozens repositories, we can observe the most popular ones. In that list, we can find a Liquibase, which is a popular tool to deploy database schema changes. We can find Dynamo, which is a visual programming tool that is sponsored by Autodesk. We can find Fauna, which is a transactional database. Awire, which is an open source communication platform. And Astro, which is a static site builder, and more. These pictures in this slide are the fixes that the maintainer introduced after we discovered these vulnerabilities. So if we sum all the users of these tools, we could reach millions of potential victims for these vulnerabilities. So the consequences of such build compromise are quite disastrous. The first major impact is exposing secrets of the vulnerable workflow. As we previously said, such secrets could be cloud tokens and other sensitive assets of the organization. The second major impact is the ability of the attacker to commit malicious code into the repository. This can cause a critical supply chain incidents, as the attacker can introduce backdoors deployed to end users or organization environments. A much smaller risk would be the malicious actor ability to run botnets or crypto miners using the runner infrastructure. To demonstrate the ability of the attacker to expose secrets, we create an intentional vulnerable workflow, which will follow us in the example. This workflow will be triggered whenever a new issue is created, just like previously. It will define an environment variable that's named GitHub token, which will get the value of the secret GitHub token. And it will have one job that's called vuln job that will have three commands. The first one is an action checkout, which basically checkouts the code of the repository and does a git clone to the repository. The second command will print the issue title and the description. We soon understand why we did this. And the third command is calling a CURL to the GitHub API and update this issue with a label called new issue. So as we showed previously, this step, actually both of these steps, both of these echoes, are vulnerable to code injections because this issue title and the issue body can be controlled by a malicious attacker. So he can insert here whatever he wants, which will run as a script exactly in this point. So the attacker could compromise the built workflow in this exact step. So let's assume the attacker can execute any code he wants in this point and explore how he can get secrets from it. The first method would be through environment variables. Because we defined the GitHub token as an environment variable in this point, which will be applied for the entire job. So the attacker could run a code in this point, which will print all the environment variables, and he could fetch this GitHub token, which will be exposed to him. The second method will be because we did the checkout for the repository code. Behind the scenes, it runs the git clone command. Whenever you're making a git clone, you're also creating a .git/config file. And with this action, it also uses GitHub token behind the scenes. It has a default parameter of a GitHub token, which we aren't seeing here. And using the token as the Git configuration. So if an attacker will print this .git/config file and search for the authorization line, decode it from base64 format, you will get the same GitHub token as we've seen previously. And he could use that token maliciously. So this is another method to fetch this GitHub token. The third possible method to do this is a bit more complex. During our research, we noticed that each such run command, before it's been run, is also saved to the disk as a shell file with a random ID. So in this example, if we print this shell file, we could see the exact run script as we can see here. And the only difference will be that these curly brackets placeholders received their real value from the GitHub Actions service. In this example, it received the real title. So how can we leverage this to fetch secrets? In the second run command, we have this secret bot token. So if we fetch and get this shell file before it's been run, we'll have this token as a plain text, which the attacker could use to his malicious needs. But as we said previously, the attacker has code execution in this run point and not in this one. So what can attacker do? Because he has full code execution capabilities on the runner, he could put a persistent script. It could be a bash script or Python script or anything you want that will listen to any changes that made to this runner temp directory, which holds this shell script. And whenever a new file is written to this directory, he could send it immediately to his controlled remote server. So whenever he reaches this run point, and this script will be saved to the disk, it could be sent immediately to his malicious server, together with the bot token. We'll soon see this example in the demo. So besides these three methods, additional methods could be applied, but more advanced one, like recording processes or inspecting memory and fetching the tokens from there. So let's see the first demo. On the left side, we'll have the attacker controlled server. On the right side, we have the victim repository. So first, we're setting the attacker server. I will sending the malicious issue to the repository. This issue will trigger several commands, and it will exfiltrate the tokens in two parts. The first part will be the GitHub token, which we'll see right now with the token. And the second part will be the persistent script that will send the run command, which we talked previously. You could notice here that in this part, we have the complete script together with the secret token, which we talked about previously. So this could give the attacker this secret and could use it to his malicious purposes. So let's see the second demo, which will show how an attacker can commit to the repository without the proper permissions. So we have a sample repository, which contains two files. We're creating a new issue. This issue will run several commands. First of all, it will fetch a malicious shell script, which will run. Then it gives the right permissions, and it also fetches the malicious file that the attacker wants to insert into the repository. After everything runs correctly, we can see we have another file added to the repository, which shouldn't be there in the first place. So now that after we showed what the possible consequences of being pipeline compromised, now let's see how can we mitigate it. We have several possible mitigations which we could apply to stop such attacks. The first one is avoiding run steps. For example, instead of running curl inside the run step, which is basically a bash script, to update a label like we did in our example actions, we can use an external action. You see the syntax here is uses instead of run. We're using an external action that, excuse me. Yeah. So we're using an external action that's called labeler, which adds a new label to the issue. It does exactly the same as this, but this is more secure. The second mitigation is to sanitize the inputs. So in our example, instead of using the issue title and body inside the run script, we could define it previously as an environment variable and use that variable in the script. With this method, even if the attacker inserted a malicious code into the title or description, this won't run, and they will be treated as a text. Another effective method would be to limit GitHub token permissions. We could add to the workflow this permissions tag, and the GitHub token will receive only read permission for the content and write permission for the issue. So even if the attacker is successfully exploited the vulnerability and gained control of the pipeline, he won't be able to commit nothing using this GitHub token. Another mitigation will be to limit secret exposure. Whenever we define secrets on an organization level, we can define what exposure each secret will have. So if we define that each secret will have specific repositories which will be exposed to it, even if we exploit vulnerabilities in the pipeline, we won't have access to these secrets. We can also apply another mitigation, which will be require approval for all outside collaborators. The default GitHub behavior is to require approval only for first-time contributors, which is a good mitigation, but a more robust one will be to require approval for all outside collaborators. And the last mitigation will be to use environment and branch protections. And an important feature in GitHub is to define environments inside the repository. These environments could be testing environment, staging, production, and each environment will contain specific secrets for that environment, and it will also be limited to specific branches of the repository. If we create an environment for specific protected branches, for example, the main branch, and we'll apply the branch protection rules for that branch, we'll have a pretty solid mitigation for these vulnerabilities. So what could be the takeaways from this talk? First, even when GitHub does most of the work for handling the build pipeline for you, including ephemeral environments and VM-based isolation, we are showing that it still can be compromised. The second one is, as we've seen in GitHub best practices paper, it delegates some of the responsibilities for securing the workflows to the developers. But we all know that developers make mistakes, so we should handle this carefully. The third takeaway would be that the consequences of the build compromise are quite disastrous and could expose sensitive secrets or cause a potential supply chain attack by committing to the repository without proper permissions. And the last takeaway would be that GitHub gives you the tool for securing the build, such as limiting permissions, secrets, sanitizing input variables, and more. We advise you to use this method. So that's it for the talk. Thank you for listening. You're all welcome to check out the full blog post with all the technical details in the Cycle blog. And now let's go for a Q&A if anyone has questions.
Awesome, Alex. So our first question reads, what are the consequences of being attacked in this manner?
Thank you for the question. As I covered, there are two main consequences for being attacked for such vulnerabilities. The first one is that your most sensitive secrets could be exposed. These secrets could vary from artifact registry tokens or cloud tokens or whatever secrets you use in your pipelines. This is the first consequence. The second consequence will be that the attackers are able to commit into your repository, into your sensitive repository without the proper permission, without having right permission. By committing to the repository, they can insert backdoors or malicious code that will be built into a package and deployed to customers and potentially cause a supply chain attack.
Awesome. Thank you, Alex. Our next question reads, what is the first step my organization should take to prevent developers from making these types of mistakes?
Yeah, so that's a good question. I especially collected all the possible mitigations for this vulnerability, and actually they're all collected and showed in the slides. So I warmly suggest if you use GitHub Actions, to go over all the possible mitigations and to see how can you apply these mitigations into your organization. Most of them are pretty straightforward and really easy to apply. For example, limiting the permissions or limiting the secret exposure or sanitizing inputs and etc.
So why do you think GitHub lets this occur? Why don't they fix it?
This is also a good question, and probably it's really hard to answer it, but probably because they can't. They can't really do that because they allow this behavior because how we call it, it's by design. They allow you to run any code you want on their build pipeline. They can't deny this malicious external injection, but they can warn you from how to avoid this situation. But my guess that they can't, and even if they could, maybe they won't. They won't have the means to deny it, to deny this possible behavior. So we all need to care from this.
So how can we be alerted when there are attacks?
It's pretty tough. The problem with the CI/CD security and DevOps and all these attacks that we only in the recent years we became alert from these attacks. So we don't have yet the means and the tools to detect such attacks. Unfortunately, I'm saying that. So we don't have many possible ways to find such attacks, but we have a lot of tools and means to deny these attacks from the first place, like to audit our configurations and to control our authorization and access for the critical system and to secure our DevOps pipeline. We have the tools to secure the complete process, but unfortunately we don't have the tools to detect such attacks when they happen because the entire ecosystem it's rather new. It's we don't have the knowledge yet how to detect such attacks.
Gotcha. Thank you. So what are other popular Git SCM vulnerabilities?
So we showed basically GitHub and GitHub Actions, but there's additional SCMs like GitLab, Bitbucket, Garrett, and more. I'm sure other SCMs have vulnerabilities as well. Just we didn't reach that yet. But stay tuned to Cycled blog and maybe we'll discover more. But currently we don't have any similar major vulnerabilities in other SCMs as well, but doesn't mean that they're not existing. That they're just not being discovered yet.
So here is a question that reads, is the real source of the vulnerability the human component?
I think it's the mix between the human component and the issue with the tools. I mean, it's not solely human component because it's not involves only social engineering, but it does involve the tools. But I think like code reviews and proper mitigations and tool integration to protect these CI/CD pipelines could mitigate this vulnerability. So I won't say it's solely on the human component because the proper tools can stop this also.
So do you see an issue, do you see this as an issue with private repos?
I've been thinking about this a lot, and I do think it is also an issue of private repos, not as big as for public repos, but it is also from private repos. Because I give you an example. Take an organization which uses private GitHub repos with private GitHub Actions, and it still doesn't give the entire organization right permissions on the GitHub, right? He will mitigate his permissions, and he will handle the authorization for GitHub and it will have only few admins and few maintainers, and even if it's private, doesn't mean that everyone can do everything. So I think it is also issue of private repos, because you don't want everyone, even if in the organization, to have a complete access to your complete right access to the SCM. You don't want to give any developer the ability to expose secrets and use cloud tokens. So yeah, I think it's also an issue of private. I mean, organizations which use GitHub as private repo should also consider this and see how they can mitigate against it.
So I'm going to put the next question up on the screen because it is a little bit long, but I'll read it out loud. So if we replace use of the run command with third-party actions, how do you recommend vetting those third-party actions to ensure they are secure and well-maintained? Doesn't relying on third-party actions just shift the possibility of supply chain attack upstream?
Yeah, so this is a pretty good and tough question. And yeah, you're right. I mean, this is shifting from one possible vulnerabilities to other, but it's complete different issue which you can control. I mean, I'm not saying to use every possible third-party action. You should always control what dependencies your repository rely on, the same way you control the dependencies of your NPM packages or NuGet packages or Maven or Gradle or etc. I mean, but it's another issue which you should take care of with the rest of your dependencies. I mean, and there are also a mitigation for it. I mean, you can use third-party actions which were marked as verified, for example. You could also clone these third-party actions and put this as a private repo and use that instead of the public one, but you won't get any updates. You could pin to the specific SHA of that action and use a specific version of it, so it won't be updated automatically, so it will be less prone to a supply chain attack. There are various methods to protect against it, but it's shifting to a different problem, which is also solvable. It's tough, but it's solvable.
So it looks like we do have one final question, so I'll throw that up on the screen as well. But would it be advisable or doable for GitHub to, at the very least, display signals to the users that what they're doing can be a potential point of exploitation?
Yeah, I would advise that, and it is doable, I think. And I guess it didn't fit to their development plan. I don't have a better answer for it, but yeah, it's doable, and it should.
Awesome. Well, Alex, we've exhausted the questions that we've received today. I'm going to give you the opportunity to let us know anything you want to before we close out today. Any final thoughts?
No, I don't have any final thoughts. So thank you for listening, and you had a really good question. And don't hesitate to reach out at me for any question you want.
Awesome. Well, Alex, thank you so much for your time and for putting together this slide deck, and really for all the knowledge that you've given us today. So I really appreciate it.
Thank you, Cody.
I would like to quickly remind our audience that this session was recorded. You can find it living on the Security Boulevard website at securityboulevard/webinars and look in the on-demand section. So on our 4 Amazon gift card winners, our first winner is Sergio D. Our second winner is Dasran M. Our third winner is Kiwanis S. And our fourth and final winner is Lucas B. So congratulations to the 4 of you. Keep an eye on your inbox to claim that gift card. And if you don't receive an email, just check your spam folder. I would like to thank SciCode for sponsoring today's webinar. And my final thanks, as always, goes to you, our audience. We really appreciate you spending your time with us today. We ask for one more moment of your time for you to fill out a post-webinar survey that should pop up on your screen once this webinar closes. But otherwise, have a great rest of your day. We hope to see you at a future Techstrong Learning webinar.